Alright guys, this will be the last video in the series about Lewis structures. This is about molecules that make exceptions to the octet rule. We're going to look at 3 different types, although really from the chem guide, the most important one is having less than an octet, so fewer than 8 electrons, but we are also going to look at examples of ions or molecules with an odd number of electrons, and then an expanded octet, so more than 8 electrons around an atom. Okay, so we'll start with an example, an odd number of electrons. So here is a molecule that does exist, nitrogen monoxide. And we can see right off the bat nitrogen with 5 valence electrons and oxygen with 6. We've got 11 electrons here, and we can see right away electrons are almost always paired, but with an odd number, it's impossible to pair the electrons. So, to draw a Lewis structure for this, it's a pretty straightforward example because there are only 2 atoms, so we obviously just put them beside each other, we put in the bonds, we end up with a double bond between nitrogen and oxygen. And then we sort of have this choice. We can keep the octet of oxygen filled and have the lone electron that's not paired on the nitrogen, or we could have the other version. The octet of oxygen is not perfectly full and nitrogen is satisfied. To pick between these 2 possibilities, we want to look at the formal charges to find the preferred structure. Okay, so the one that minimizes formal charge. So if I'm going to do that, reminding you of that idea of calculating formal charge, I'm going to look at the number of electrons that nitrogen brought to the table. So that is 5. Nitrogen is in group 15. It has 5 valence electrons. And nitrogen also has 5 assigned electrons in this diagram. So that means its formal charge is 0. Similarly, oxygen has 6 valence electrons. Normally it's in group 16, and in this diagram it is assigned 6 valence electrons. So the formal charge is 0. That's pretty good. So I believe there and there. And then over here we've got nitrogen comes with 5, assigned right now 1 for each of the electrons shown in a pair, and then 1 from each bond gives me 6. So 5, the number of valence electrons it normally has, minus 6, the number that it's assigned here, that gives me a formal charge of -1. And then oxygen normally has 6. It's depicted right here with only 5, so it's got a formal charge of +1. Okay? So then between that, we've got this version right here that minimizes formal charge. This one that has, so these formal charges are 0. This one has formal charges. So obviously this over here is the better Lewis structure. Okay. Let's look at a couple examples where we have fewer than 8 electrons. So I want to put a little disclaimer in here. There's an element that we haven't talked about yet. It just hasn't come up in an example, but hydrogen is the obvious exception to the octet rule. It only needs 2 valence electrons to be satisfied or make a stable molecule. Okay, so it's the most obvious exception. Other exceptions are going to include boron, which is pretty okay with only 6 electrons, and then beryllium, which we normally think of as a metal anyways, but it will create molecules if we look at the bonds on that polar versus non-polar versus ionic scale. The bonds that beryllium makes with nonmetals are usually in the polar covalent range. And beryllium makes molecules, it only needs 4 valence electrons to make stable molecules. So here's an example of a molecule that where we see fewer than 8. And this is a stable molecule. It exists, boron trifluoride. So boron, being in group 13, brings 3 valence electrons. Each fluorine brings 7. So this Lewis structure totally works. Now, you might wonder, the octet rule is always the rule we've gone by. Isn't there a way that we can draw this molecule with boron with 8 electrons around it? And you'll see that right here. So if we put a double bond between the fluorine and the boron, then we do end up with a satisfied octet on boron. Now it has 8 electrons around it. But if we look at the formal charges, now we're giving boron a formal charge of -1, we're giving fluorine a formal charge of +1, and there are resonance structures here, but that's the case in all of them. In each of these, obviously, boron is going to have a formal charge of -1. And what we find, because of those formal charges, is that this is not an accurate picture of the distribution of electrons in boron trifluoride. Okay? And there's actual empirical evidence to back this up. It's not just people kind of waving their hands around and being like, oh, minimize formal charge. That's the right way to do it. But it's true that boron tends to form molecules where there are, where it has fewer than 8 electrons around it. So 6 valence electrons, like so. Okay, so moving on. Let's look now at a few examples where we have an expanded octet. So an example, phosphorus pentachloride is shown right here. So phosphorus, you can see very clearly that phosphorus here, it's got 5 bonds around it, meaning that it has 10 valence electrons in this molecule rather than the normal 8. And we will look at some examples where we have 10 valence electrons around the central atom, and we'll also see some examples with 12. Okay, so just the only way to make this work is to give phosphorus 10 electrons. That is the Lewis structure that works. And in general, if that's the case, if you have way more electrons than seems reasonable based on the rules that we started with for Lewis structures, if you have an element that's in period 3 or lower, then you're allowed to expand its octet. So either phosphorus or chlorine could have an expanded octet. In this case, because phosphorus is the central atom, it has lower electronegativity. It is the one with the expanded octet. And this point right here, it's related to atomic theory, which we're going to get to later in the course, but these idea of orbitals, phosphorus has these bigger d orbitals that probably allow it to have more than 8 electrons around it. Now, there are some cases where we might draw a Lewis structure that follows the octet rule, but there's a version of that Lewis structure that breaks the octet rule but is in fact a preferred Lewis structure. And this, what we're seeing right here with a phosphate ion, is a case like that. So all the formal charges have been assigned here. You might want to pause the video if you're still working through that idea of formal charge and double check these values. But here we can see that every atom has a formal charge, whereas here there's only 3 atoms with formal charge. So this structure with the expanded octet on phosphorus does minimize formal charge. So that's what that text right there says. Okay, and what we can take for this if we want to sort of generalize what's going on is if the central atom is in the 3rd period or lower, then we should expand its octet if it eliminates some formal charges. Okay, so that tells us that this is the better structure. And that's it. End of slideshow. Okay, so I'm going to post this up for you guys. The next thing I need you to look at, well, before you move on to the next set of videos, there is a document posted. Some of you who are in class picked it up already. It's called Predicting Molecular Geometry. And I need you to go through that, and for each molecule that is given, I want you to draw the Lewis diagram for it, okay? So it's a big table. There's lots of things to fill in, and that's what we're going to do in the next set of videos. But I would expect you to have the Lewis diagrams done first, just so the videos don't have to be a million minutes long. Okay, so go through, fill in those Lewis diagrams. Ideally, you'll either have a copy that you got from me, or you'll be able to print it off because it's posted here, or you can just do them on your own table that you make on your own paper. Okay, but I'll see you in the next series of videos, the VSEPR theory videos.